All right. So you can see, so the double hashing, you need to use two hash functions, right? Yeah. All right. So first, let's look at our current problem. Here, so let us use that quadratic hashing method. So you can see for this part, although there is a variable I corresponds to the number of childs, but this whole function is a fixed function. Fixed function. It always like this. So the function is it never changes, always like that. That could be the problem. That may be caught by some pattern. Yeah. All right. To break the pattern, we want to break this part, fixed function part. So we will use a second hash function to replace this fixed function part to break some pattern, right? Yeah. So the design of new hash function in this way. H1, the first hash function, H2, the second hash function, then mod n. Using this way, to improve the problem. Primary clustering problem, secondary clustering problem. In this design, we use two auxiliary hash functions. So that's why we call it double hashing. Why this new method is better than the old method? How can we see that? So we use one special view to see why this double hashing is better than quadratic hashing. We use number of probe sequences. Number of probe sequences. We study that. All right. So let's look at the linear probing and quadratic probing again on this property, number of probe sequences. Yeah. For linear probing, so this is the linear probing hash function. Quadratic probing, this is the quadratic probing hash function. Yeah. Let's compare two probe sequences for two keys. Yeah. So two probe sequences. Yeah. The H can be used for linear or quadratic. You have to use the same hash function, but you can use either linear probing or quadratic probing because in this aspect, they have the same property. All right. If the first two values are the same, we consider this situation. The first two values are the same. That's possible. Let's look at what would happen. First value of two sequences are the same. Then you will see the second value of both parts, they are the same. Either you use the linear hashing function, quadratic hashing hash function, same value. So that means the second number in the sequence also the same, and so on. So all the remaining numbers in the sequence all the same. That's not good. So that means the first number in the sequence determines the whole sequence. The first number in the sequence determines the whole sequence. So that means when the first value is fixed, the whole sequence is fixed. That's a not good property. So you do not have the flexibility to choose different value. That's the problem that caused the clustering problem. Okay? Yeah. So the first number fixed, the remaining, because there is a pattern, right? Because the whole sequence is fixed. So there is a pattern there. So we want to break that pattern. Okay? All right. So how to break it? Yeah. You can see with this property, the number of probe sequences determined by the first value. Okay? How many different first values do you have? Only n. That means the total number of probe sequences is this number. This number. That's a small number. Yeah. So let's look at the double hashing case. Do we have more number of probe sequences? Yeah. Double hashing. Yeah. So this time we have these two hash functions. Yeah. Then let us compare two probe sequences for two different keys. Okay. All right. If the first number in two sequences are the same, can we get the similar thing as the previous one? Let's compare. Okay. So let us compare these two function values. Are they the same? Yeah. So let's look at a different part. Because the first term of two numbers are the same. Now let's compare the second term. Second term. Okay? I part is the same, so we do not look at the I part. Let's look at the H part. H part for two different keys, same or not? In general, different. In special cases, they could be the same. Very special case. But in general, they are different. So this tells us then for the remaining numbers in the sequences, most of the time they are different. Only in rare case, they could be the same. Very rare. Not like the previous method, they're always the same. Okay? So that's different. Yeah. So now you can see how do we determine a whole probe sequence? These two numbers. We need these two numbers, not just one number, two numbers to determine the whole probe sequence. Okay? Then we will have more number of probe sequences. Yeah, because two components we can use to determine the whole probe sequence. So the total number of probe sequences for this situation, m squared. Okay, so we have freedom at two components. The first component gives us m different choices. The second component also gives us m different choices. So we combine two components, we get m squared different choices. So much larger than the older method that gives us only n different choices. The more probe sequence choices we have, the better the overall performance. Okay, so the collision problem will be much less severe with larger number of probe sequences. With smaller number of probe sequences, the collision problem will be more severe. Okay, so that's the basic analysis. So you can see double hashing method much better, right? So finally, we find one that performs pretty good, so we can take it. All right. At the end of this part, I want to use one of our old problems related to this topic. So let's revisit our problem number 5, element uniqueness problem. Okay. Given an array, how to check if all the elements are distinct. All right. Let's recall how did we solve this problem a long time ago? How did we solve it? Okay, remember, we use sorting. Remember, so a better algorithm we use to solve this problem, we use sorting. We sort the data first. In that method, we have big theta of n log n efficiency. So that's what we can do before. Now, after we learn the hashing method, can we do better than this? Right? Better than this? Yeah. So that's the goal. Okay. All right. So examine the value of the elements. Can we assume the values are strings? Yeah. Now, we can treat the value as strings. Yeah. Special type of string. Okay. Yeah. Now, this time we can build a hash table to store the array. Hash table, hash function. So then we can store in the hash table, hashing, right? Collision. So we have, although much more complicated than before, but there is a method we can do in that way. Okay? All right. Now let's consider the cost. How much the cost we need to build a hash table? Big theta of n. That cost to build a whole hash table, that's the cost. Okay, so one element, one by one, we hash it into the hash table. Okay, yeah. How to detect if a value is repeated? Yeah. Because to solve the problem, we go through the array element one by one. Yeah. When we build hash table, we go through. Yeah. So here, the same procedure. So we run the hash table building procedure when we process this whole array. During this running procedure, we can determine if one element is repeated or not. Okay, yeah. If a value can be hashed successfully without collision. Okay, with collision, yeah. So let's see. Without collision, that's fine because it's a new value, right? Without collision, it's a new. Next, with collision. Okay, so two cases. The first, with a collision. Second, without collision. Okay, without. A collision. Okay. Without collision, it must be a new value, right? Because it takes a new slot. So the value must be unique. Okay, so without collision, we have no problem. But with collision, there are two cases because two different values can be hashed to the same slot. Okay, so with collision, then we compare the values first. Okay, yeah, because you hit some element, then let us compare their values first. If they are the same, then we find a repeated element. If they are different, so let's go to the find the next location, next slot. If another collision, compare the values. If the same, we find it. If different, let's try another one. Okay? So in this way, you can detect if there is a repeated value. Okay? Yeah. The whole cost on average. So we say the average case performance is this. Not that. Okay? So this method is more efficient than our sorting method. We do not need to sort. Okay? So we build a hash table. Okay? Although when we build a hash table, the overhead is a little big, right? Yeah. We need to do a lot of preparation. So that's the overhead part. But after that, then when we check if element is unique or not, then it will be fast. Okay. All right, so we find a better solution for our old problem. So we complete this hashing topic. Okay. Next, we have another important topic, decision trees topic. Very important. So I want to use a lot of time to discuss that decision tree topic. All right.